Hello, this is my Physics 2211 Lab 5 presentation. The purpose of this lab was to characterize the burn of a solid rocket motor and simulate its performance across multiple fields. The principles used in this lab were the energy principle, isentropic flow equations, and the thrust equations. A MATLAB program was used that simulates the burn of a rocket motor given the shape of a solid fuel and the diameter of the nozzle throat. The results were that energy is conserved from the combustion chamber to the nozzle exit. The physical principles used in this lab were the energy principle, the flow isentropic relations, and the thrust equations. The energy principle relates change in energy to work and heat. It was used to show that delta E equals 0 in the system. The flow isentropic relations were used to relate various nozzle conditions to one another and used to find exit velocity, area ratios, exhaust temperature, and more. The thrust equations were used to calculate the thrust produced by the motor at a given time. This is a model of the solid rocket motor that this sort of simulation simulates. The hollow cylinders in the middle are the solid fuel grains, which are much of what the inputs are designed around. The system in this experiment was the solid rocket motor and the Earth. The surroundings were nothing significant. The initial conditions were that the grain inner diameter was 1.8 inches, the grain outer diameter was 3.239 inches, the grain height was 7.5 inches, the number of grains was 5, and the throat diameter was 1.25 inches. The assumptions were that the burn follows isentropic flow, meaning that it's adiabatic, so no heat is lost to the surroundings, and that no friction is encountered by the gas hitting the nozzle. The burn rate is assumed to be constant at all points in the exposed burn area, and the combustion products are assumed to obey the perfect gas law. The simulation structure follows this sort of system. We start with our initial geometry and calculate the burn area, use that to calculate a few things like chamber pressure, which then we can update our geometry by calculating burn rate. And then with the new geometry, we check, is there still fuel? If there's not, we end. If there is, we repeat. And we store data at each increment. This is a few of the main segments of the program. On the left are many of the functions that are used to calculate many of the variables used. The middle picture is the main while loop. As you can see at the top, there is the condition that checks if the fuel is still there, and it goes through and calculates many of the variables before storing them in a data. On the right is a list of the final calculations, where many of the variables calculated there need to have all of the data from the while loop to get the correct answer, like the maximum chamber pressure. Here are the results from the code. We have 3 graphs that show chamber pressure versus time, thrust versus time, and mass flow versus time. And then we have multiple outputs that characterize the burn of the motor. So some similarities, differences, and sources of error. So pressure spikes are caused by small bubbles in the propellant, which can cause uneven burn areas and quite large jumps in chamber pressure. Our assumptions are, at the end of the day, assumptions. They are made for an ideal world, which is not the one we live in. For the propellant, it could not burn all of the way. There could be small particles left. And non-adiabatic flow, meaning heat, could be exchanged with the surroundings, meaning that it's not a perfect energy transfer from the combustion chamber to the nozzle. So what does it mean for energy to be conserved here? In the combustion chamber, there are extremely high pressures and temperatures, but relatively low velocities. The nozzle is shaped in a way so that when the flow exits the nozzle, there's relatively low temperature and pressure, but much higher kinetic energy. What if your solid fuel is in a different shape? The burn rate in the simulation is dependent on how much surface area there is of fuel at one time. If you have a different fuel shape, you would need to design an iterative function to calculate the new burn area for the shape each time step. Thank you. Have a good day.